A lot of space agencies over the past decades, they've put a lot of different satellites into orbit that are basically observing our Earth to learn more about how are our sea levels rising, how are the glaciers melting, how much deforestation is happening. And basically, those are our eyes in space, and they help us learn how we can deal with problems that we will have in the future because of climate change. And if we now have interference, then we will lose all this information and it will make it much harder to deal with this problem.
Hi, I'm Stephanie Tomapos, and you're listening to Down to Earth, the show where we talk to incredible geoscientists about their science and its impacts on our planet. Today, I need to reveal an uncomfortable truth to you. You are interfering with remote scientists' ability to read satellite data. Yes, you. How so, you ask? It all comes down to electromagnetic waves, otherwise known as radio frequencies. This episode of Down to Earth comes from the Frequency Allocations in Remote Sensing, or FARS Technical Committee, of the Institute of Electrical and Electronics Engineers Geoscience and Remote Sensing Society. The FARS Technical Committee's goal is to interface between GRSS and the radio frequency regulatory world and keep track of spectrum allocation issues that impact the geoscience community. To learn more about this technical committee and how you can get involved, visit their website at grss-ieee.org/technical committees.
So my background is electrical engineering, and on a daily basis at DLR, my work basically involves the performance estimation of synthetic aperture radar satellites, so satellites that we are using for Earth observation.
This is Dr. Tobias Bollian. He's a research scientist in the Microwaves and Radar Institute of the German Aerospace Center, also known as DLR.
After my master's degree, I did a traineeship at ESA on the biomass team, which is a satellite that is going to be launched in the next few years to basically measure our rainforests and biomass all over the world. And during that traineeship, I learned that there is this problem, radio frequency interference, and that it's a big problem because we don't know how much interference to expect once the satellite is launched. And I was very fascinated with this problem. And I decided to pursue a PhD in this area to see how future SAR systems could basically deal with this kind of problem.
As Tobias mentioned, radio frequency interference is a major barrier facing remote sensing scientists today because interference from communication satellites, wireless devices, including our cell phones, and more make it really difficult to interpret satellite data gathered from the radio spectrum. As Tobias explains, this can have huge implications for our ability to make decisions about pressing issues such as climate change. So what is radio interference and what tech and natural phenomena causes it?
Radio interference is basically a side effect of the fact that the radio spectrum is of finite nature. So if you have two signals or two electromagnetic waves that are being transmitted at the same frequency and at the same time, then what happens is that those signals, they mix together and overlap at the receiver. So you can't tell them apart. So you can compare this, for example, to, let's say you're in a big room with a bunch of people and there's two people that are rapid fire talking at you. And then you can't really differentiate what is the individual person saying. On the other hand, if they are taking turns speaking, or if that second person is far away on the other side of the room and talking to someone else, then that's not a problem. This is basically the same thing that happens with radio interference. So if two different signals are being transmitted at the same frequency, then it's really hard to differentiate them.
So what kind of tech and natural phenomena causes it?
So it's mainly other services. So for example, for our remote sensing satellites, we operate in a specific frequency band. So once we operate in a frequency band and there's now, let's say, a communication satellite that is operating in the same frequency band and is communicating with stations on the ground, then we can also see these signals if they are at the same frequency, and then we have a really hard time filtering them out of our data. For example, from one day to the other, we lost entire coverage of Japan because in Japan they deployed a new TV receiver throughout the country, and then the entire country was basically corrupted by interference signals.
Wow, how did that happen?
So to my understanding, there was a problem with the hardware of all those TV receivers that were basically distributed to the people. So it was leaking into the frequency band that it was not supposed to leak into, even though it was transmitting at a different frequency, but it leaked into the radar's bandwidth.
I can't believe that a TV receiver caused scientists to lose their remote sensing data from Japan. That's just crazy to think about. How does radio frequency interference, or RFI, happen so easily? Can you give us a breakdown of the radio spectrum? How are remote sensing scientists using it to understand our planet?
Of course. So, what is the radio spectrum? So, basically, the radio spectrum is part of the electromagnetic spectrum. And what it means is in physics, we have those electromagnetic waves, such as, for example, as you've heard, visible light is an electromagnetic wave, or also your mobile phone, the way it sends and transmits signals is via electromagnetic waves. And those waves, one property, how you can describe them, is a certain frequency. So basically, it means that the electromagnetic spectrum is basically just a big catalog of frequencies. And if you look in this catalog, what you can see, the visible light, it has a very high frequency, so it's located very high up in this spectrum. And if you then move to lower frequencies, past the infrared light, then you will end up in the radio spectrum, which is ranging from about 3 hertz to 300 gigahertz. And that is all the frequencies that we call the radio spectrum. One fascinating thing that we can do with electromagnetic waves is if we have a satellite in orbit, we can put an antenna on the satellite, and then we can use the satellite to send an electromagnetic wave to the Earth, and then we can just see what happens, what is being scattered back to the satellite. Or in the case of the passive radar, we can just see what are the natural emissions that are coming from Earth. And in this way, if we do some processing, we can gain an image, and this image tells us a lot about what is going on all over our planet.
You mentioned active and passive radar. What are the differences between them?
So in an active radar, the word active implies that this active radar is transmitting pulses to the ground, and then it's waiting for those pulses to come back to the radar, and then it can extract information from those pulses. So it's basically using its own source of illumination to gather the information. Versus in passive radar, we're not transmitting anything, we're just listening, because every body on Earth is having some natural emissions, and this is something that we can use to also gain information about it. And this happens also in different frequency bands. So it basically it's a complementary band that we can use to gain more information. So active and passive radar can also work together to get a better insight.
So basically, I emit some radar.
Yes, basically it's having some natural emission that can be picked up by a passive radar.
All right. That gives us a good explanation of what is passive and active. So, what is the current status of radio interference on Earth?
So there have been a lot of different studies with different sensors and in different frequency bands. So for active radar, there's one study that was performed over some area in Canada where they between 1996 and 2012, they basically observed how much RFI is in this area. And they noticed that over this time frame of 16 years, the RFI amount doubled. But it was not really quantified in consistent ways that we can use it also for different sensors. That's basically only what we know. So we don't really know how much there really is.
Mm-hmm. Why does this all matter? Can you give us an example of how radio frequency interference might impact the average person?
Yes, so for example, a large part of the bands that are used for the weather forecast are microwave bands. And with these, we've been able to improve the forecast capabilities from decade to decade. And if we now take away some microwave bands because we have a lot of interference in there, then the predictions of the weather get worse. I also watched a talk a couple of years ago that was very interesting by Stephen English from the EMCWF, from the European Center for Medium Range Weather Forecasts. And so he showed some simulations for some cyclones. What happens with the prediction models if you remove some microwave bands because you lose them with interference? And in one example, the model then falsely predicted that the cyclone was landfalling on Florida. And that would have resulted in a false alarm emergency evacuation, which then, of course, would have resulted in unnecessary cost and trouble for a lot of people. But then he also showed another example where now instead of having a false alarm, instead of falsely saying that it would hit Florida, it was now not able to predict that it was hitting Florida until 6 hours before. Versus if you had the microwave band, you would be able to predict it 12 hours in advance. And 6 hours more time to evacuate and make sure that there is fewer property damage and everything. That also directly translates into saved lives or costs saved by the government. So I thought that was a very good example how you can see how this has a very big impact even in the short term.
After the break, Tobias tells us how we can help deal with radio frequency interference issues. So stay tuned.
Are you looking to make an impact in geoscience and remote sensing science? Then consider joining one of the Geoscience and Remote Sensing Society's technical committees. From environmental analysis to spaceborne imaging spectroscopy, each technical committee advances innovative research and technology in a specific field of remote sensing. By joining, you'll connect with a community of passionate researchers and professionals who are fostering important international collaborations and steering global research agendas. You'll also gain access to the latest news and state-of-the-art research in the field. Expand your network, enhance your career, and make a difference. Join a GRSS technical committee today by visiting grss-ieee.org/technical committees.
Welcome back. Today, we've been speaking with Dr. Tobias Bollian, research scientist in the Microwaves and Radar Institute at the German Aerospace Center, about radio frequency interference, or RFI. As Tobias explained, radio frequency interference occurs when two electromagnetic waves that are being transmitted at the same frequency mix together. This blending of signals prevents scientists from being able to properly interpret radar data, which, as Tobias illustrated, can have major implications on our ability to properly detect and respond to things like natural disasters. The problem with radio frequency interference ultimately lies in the radio spectrum's finite nature. There are only so many radio frequency bands, and with our increasing use of wireless technologies, the radio bands are getting pretty crowded with signals. So, what can we do to ensure the radio bands needed for monitoring climate change remain free of interference? Here's what Tobias had to say. Obviously, wireless technologies aren't going away anytime soon. And you just talked about why it's so important for scientists to have access to these bands without interference. So, in your view, how do you think we'll deal with RFI in the future?
Yeah, so that's a good point. How will this look like in the future? You just said yourself that those wireless devices, they're not going away. Actually, the demand for wireless devices will grow in the future. And also, those devices, they don't only occupy a single frequency in the frequency band. So the more information you want to transmit, so for example, if you want to have faster internet, or if you want to have more TV channels, or the TV channels shall move from HD TV to 4K TV. So the more information you want to transmit, the more bandwidth the signals needs to occupy. So not only will there be more devices, they will also occupy a larger amount of the frequency spectrum. I think there's two important aspects for the future of RFI and remote sensing. First of all, we have to make sure that we don't lose those bands to RFI, that there's not services that are allowed to be transmitted in those bands. But also, we will have to find ways to be more efficient. So, for example, what I could imagine in active radar, that instead of competing with a radar satellite and a communication satellite in the same spectrum, that we could, for example, maybe combine them on the same platform and use the same signal that we use for sending the information to people on the ground to also measure what we want to do with remote sensing. In passive radar, this would not be possible because passive radar wants to measure the natural emissions of everything that's on Earth. But maybe here we can have some time sharing where this would be a lot of effort, but I could imagine that every time a satellite is flying over a specific region, that then all the receivers and transmitters on the ground that are using that frequency band, they have to hop to a different frequency so that this band is now free for the satellite to observe. And once the satellite is out of reach again, they can continue using that band again. So I think the future would be about efficiency in that sense, because it's only going to worsen otherwise.
What about political advocacy to reserve bands for scientists?
So what's already a thing, and FARS is also working on this. So FARS sees itself as an interface between the remote sensing world and the spectrum regulatory world. And there's different organizations that manage the radio spectrum. So on an international level, we have the International Telecommunication Union, ITU, and there's also national entities. So in the US, it would, for example, be the FCC. And what they do is they manage kind of a rule book called radio regulations, which basically tells us what frequency can be used by which service and in what country and how strong can those signals be. And this rulebook, it's constantly evolving. So every few years, they are making changes at a conference called the WRC, the World Radio Communication Conference. And there's also many smaller meetings in between. And then what basically is being done is somebody is proposing changes to the radio regulations, and then people are performing studies in between those big conferences to see how would this change impact existing services, how would the interference increase to those services to make sure is this an acceptable change or not. And FARS is also actively participating in that to make sure that the voice of the remote sensing community is being heard. But this also only then applies to the official rules. But unfortunately, there's also interference that is illegal. And that is very hard to get rid of if somebody is transmitting in a band that he's not supposed to. And it will still affect our data.
You mentioned about illegal interference. How big is that problem? Do we have a lot of illegal interference?
Yeah, so when a couple of years ago, ESA launched the SMOS satellite, they were very surprised by how much illegal interference was in this band that was supposed to be listening only, basically, for passive radar. And they've done a good job of tracking a lot of those interferences down and shutting them down with local governments. But it's a very difficult and hard process. It's very time consuming. And in the first place, they shouldn't be transmitting at all.
Who knew illegal interference was such an issue? And I'm just glad something is being done with that. So, going back to what we can do to reduce or prevent radio frequency interference, you mentioned what the Geoscience and Remote Sensing Society's Technical Committee, FARS, has been doing with respect to rules around radio regulations. What else is being done?
So one activity that we just recently started is that we started with developing a standard, which is basically trying to find objective measures how we can quantify the quality of all those Earth observation frequency bands in terms of man-made RFI. So how much RFI is there? So that, for example, space agencies can report based on these quantitative measures, how much RFI are they seeing? And then we can try to find a way to compare different sensors and different frequency bands, just so we can see how does RFI evolve over time. And maybe we can even apply this also to archive data to get a better sense of how it has been going on so far in the past. What FARS is also doing is, so we're organizing a lot of different sessions at different conferences about RFI, where researchers can present what work they are doing on how to get rid of RFI, or at least try to get rid of RFI, because it always comes at a sacrifice. And we also have lectures where you can learn more about it.
And what about the average person? Can I just reduce my use of cell phones? Is that going to solve the problem?
So if everybody would do this, sure, then maybe it would have an impact. So we could say, okay, we don't need this communication satellite because we don't want those TV stations anyway, or something like that. Or we don't need a fleet of satellites to broadcast internet. We just can get it via fiber cable or something like that. Then sure, but I think that's probably not going to happen, that everybody would, work together like that. And if just a few people reduce their bandwidth in that sense, I don't think that would have too much of an impact.
So in your view, what's the best way to deal with radio frequency interference?
The best way to get rid of radio frequency interference is to make sure it doesn't happen to begin with, so that you don't either lose data or lose image quality or need a complex system. So hopefully in the future, our satellites, our remote sensing satellites, will continue to provide good data. Otherwise, we would be blind and we wouldn't be able to know how is our planet changing, how is the sea level rising, are the glaciers melting. So we would be blind with fighting climate change. So I hope that in the future we will manage to keep interference out of these bands and continue to do great science with it.
Well, that's all for this episode of Down to Earth. To learn more about radio frequency interference and Dr. Tobias Bollian's work, visit the FARS Technical Committee website at grss-ieee.org/technical committees. Don't forget to follow us on Spotify and Apple Podcasts, and give our sponsors a follow at IEEE_GRSS on Twitter and Instagram, and IEEE Geoscience and Remote Sensing on Facebook and LinkedIn. This episode was produced by Nicole Bedford from Nicole Bedford Films, with help from me, Stephanie Tumampos. Graphics and design by Mylene Briggs of Killam Media. And a special thanks to Fabio Pacifici and Keely Roth for their support. I'm Stephanie Tumampos, and you've been listening to Down to Earth.